Hey, this is Angie with Beyond the Lecture, and today I am going to take you through ionic compounds and how to identify them, how they're formed, and also how to name them and derive formulas from a name. So first things first, I want to discuss really quickly why I put this video out first. So I have a video that I put out maybe a week or so ago that talks about some important things you need to know in chemistry or concepts you should have a good handle on, and naming is one. And why is that? Because it's an reoccurring theme in chemistry, being able to derive a formula from a given compound name and then doing additional work with it, whether it's putting it into a balanced equation and then doing maybe some further analysis like stoichiometry, or maybe doing some solution chemistry with it. And I've noticed in working with my students over the past couple decades that it seems that if there's a struggle with naming and handling the naming part, everything kind of goes downhill from there, maybe, or there's just if you don't overcome that, you're going to have issues. So I'll leave it at that, and I'm going to hop into the basics of ionic compounds. So ionic compounds are part of the bigger picture. Is there are two major classes of substances or compounds in the chemistry world that you look at. One is ionic, and then the other is covalent. And the differences are simply in how these elements either share or transfer electrons. And the idea is that in the ionic world, metals, which we ultimately they end up being cations, give away electrons, and the anions will receive those electrons to form positive and negative charges. So cations have the positive charges, anions have the negative charges, and they have formed this electrostatic force that keeps them together and keeps them, basically what helps them form these compounds, and they stick together and exist in nature. So there's the general definition, and I have these notes out on my website, so please feel free to go out and print them and review them during the video. That's the basic definition. So by definition, ionic compounds, they are composed of ions, so ionic ion, right? And the metals, you'll see noted there, metals typically form the cations, non-metals form the anions. So we are going to take a quick trip over to the periodic table and talk about the different types of elements that we have on our periodic table. So we'll largely focus today on the metals, which are on the left. So that's going to be group 1 and group 2 right here, group 1 and group 2. And then we also have transition metals. That's basically this big old chunk right here in the middle. We'll deal with those here in a separate video, but transition metals can have varying, in chemistry we call it varying oxidation states, but they can have varying, certain elements or metals in the transition area can maybe give away 1 electron, or they could give away 2, and we have to designate that in the name. So we'll cover that in a separate video. We're going to basically be covering group 1 and 2 for the metals, and then group 3, which I will check over here, and all the way down to 17, right? So traditionally we look at those groups as 13 through 17. We traditionally look at them as 3 through 7. And these numbers represent how many electrons are available in the very outer shell of their electron configuration. And so it gives us an idea, each column or group, okay, gives us an idea of how many electrons they will either lose to become cations or gain to become anions. So just know that group 1, typically they have 1 single outer electron that they tend to lose, and group 2 will have 2, okay? And that means that when they lose these electrons, they'll form a positive charge because their electrons and protons in the nucleus will be, they won't be in balance. So they'll have a net charge. They'll no longer be zero. So with group 1, again, we have a +1 charge. Group 2, that's your beryllium. And down to radium, they will gain a +2 charge. And then on the other side of the periodic table, we have commonly boron and aluminum. Is what you'll see on problems. Boron will lose 3 electrons, as well as aluminum, to gain or to result in a +3 charge. Carbon is this group right here. I'm just going to delete that circle. So carbon is group 4, right? And all their elements down the line there, down the group. Carbon is it's a nonmetal, and it generally combines with other nonmetals in a covalent sense. So, and not to say you won't see it in the ionic world and naming convention. I think it takes the last name, carbide. Okay, so not often you'll see it, but you'll be seeing carbon more on the covalent side of things. So just FYI. We also have the final 3 groups, 5, 6, and 7, or 15, 16, and 17. Those are nonmetals that typically gain electrons to complete their octet. So typically these elements want to gain a more stable configuration of 8 electrons in their outer shell to make it more stable. Okay, and groups 5, 6, and 7 will add their charges respectively of, once they gain all their electrons, of -3, -2, and -1 charges. Okay, so 5, 6, and 7 represent the number of electrons in their outer shell. We also call that the valence shell. And then the negative charges just reflect, the charge that they'll have once they take on those extra electrons, and change the overall net charge of how they are existing. So again, metals are on the left-hand side, and they also populate the inner part, the transition part, which we'll get to later, some more examples later in a different video. And then we also have nonmetals. Those are all the guys on the right-hand side. And you'll notice we have more metals than nonmetals. Okay, so just interesting little tidbit. I just want to give you an overall view of how we assign charges to these cations and anions. And over the years, when I meet with students, typically their teachers have already walked them through this, and they already have the designated charges written down. So I'll go ahead and add +1, +2 over here on my periodic table, and I got this from ptable.com. It's been my go-to for a while. And so, yeah, we'll generally have +1, +2 on the left, and then -3, -2, -1. And yeah, we typically put plus or minus 4 for carbon, but we'll talk about that more on the covalent side of things. So there you have it. You can get that periodic table at ptable.com. You can fill it into your liking, or I'm sure your teacher or professor already gave you something like that. So we're down to, I've already gone over, how do you find the ions, right? How do you find the metals versus the nonmetals, and some common examples. And then we already discussed the octet rule. So typically metals lose, they become positive, and then nonmetals gain, they become negative. They gain electrons. They gain negativity to be more negative, right? They'll go below, have a charge below 0. So an example of an ionic bond forming between 2 atoms to make a molecule, ionic molecule. This is a very classic example in chemistry. I would not be surprised if your teacher or professor walked you through this example. We have sodium and chlorine to form sodium chloride. And this is what we call our typical table salts. And as an FYI, ionic compounds are typically called ionic salts. So they exist in some type of salt-like crystalline form, okay? So that's just an aside. But going back to sodium and chlorine, they combine. So, sodium loses one outer electron. And because it now has 10, it'll have 10 electrons and not 11 electrons. Plus it'll have 11 protons in its inner core, its nucleus. It's going to have an overall net charge of +1 because it has that extra proton that's not balanced out. And then with chlorine, so if we look at the nonmetal side, we have chlorine having 17 electrons. It'll gain to have 18, but it's still sitting at, we're not touching the nucleus, right? We're just adding electrons on the outer part of the atom. We're going to have a -1 charge there. So 17 minus 18, that's at a -1, and there's your charge. So I have a +1 charge on sodium, -1 on chlorine. Guess what? They combine. They basically combine Na+ and chlorine minus combine to form NaCl. So that's how we write the proper compound name. We put the elements together. Metal comes first. The nonmetal comes second. And then as far as naming goes, and I'll go through the naming routine here below. I did want to point out, though, that I did shorthand the charges. So you can have, I'll put it up here in blue. I wonder if you can hear the wind out there. Wow, the weather's pretty bad here. What I wrote in blue on the top, those represent the same thing. So plus it's implied it's a +1, okay? Same with the negative. So with chlorine, you can have that. Okay, you can have 1 minus or -1. I'm not even entirely, I've been doing this forever, but I don't think there is a difference. Like teachers and professors aren't going to get after you for this using either or convention. But just know you can have +1, 1 plus. It all means the same thing. We get the idea, right? So going down to the actual naming, right? So if I see, for instance, NaCl, and that's actually my first example here. If I see NaCl, I would first identify it as ionic, and I would notice there's a metal and a nonmetal, of course, points to ionic. And you basically name the metal first. You don't change it. Don't do anything to it. You don't modify it. And then you note the nonmetal second, but you just need to drop the ending and add "ide." Okay, so chlorine, ene goes to "ide." Bromine goes to "ide." And then our third example here, we have aluminum tied to nonmetal oxygen. And so, I don't know, I guess that's oxygen. I guess we're eliminating the egen and just adding "ide." Oxide, that's most students are familiar with that particular naming. Oxide. It's in a lot of cleaning materials, things like that. So polyatomic ions. So we're here. We basically I've taken you up to the point where you could name an ionic compound given the formula based on the atomic symbols and knowing you're looking for metal and a nonmetal. However, please note, binary, keyword being binary, that means 2. So we have 1 metal, 1 nonmetal. Okay, those should be fairly easy to spot. However, we now have polyatomic ions to deal with. So poly means many. So polyatomic just means a combination of 2 or more atoms, okay, to make what we call functional unit in chemistry. And they basically hang out together and are basically, they don't separate. Basically, they generally stay together in their form. So for instance, I'll give you some common polyatomic ions. Your teacher will give you a list of probably anywhere from 10, 15, 20, maybe even more of polyatomic ions that you need to be familiar with in your chemistry course. Your job is to know whether you need to memorize them, like they might give it to you on the quiz or test, so you don't have to memorize the formulas and the charges that are associated with them. You'll notice this example right here, I give you some common polyatomic ions, only 5. Sorry, I don't want to give you the whole list because I don't know which particular ones your teacher wants you to know. I have a rough idea, but let's let the professor or teacher communicate that to you in their class. But for instance, ammonium, very popular. It's a very common polyatomic ion. Notice it does have a +1 charge up here, and it's derived from ammonia. Ammonia is this guy right here. It's common in household cleaning materials, things like that. We add a hydrogen, we have an NH4 plus charge. Sulfate and sulfite, they both carry a 2- charge. Nitrate and nitrate carry a -1 charge. Now notice we're taking away the ides, right? When you think of ide, think of your binary, right? Your 2 elements up there that we talked about earlier. I'll circle there in the video. When you come across polyatomics, they're going to have 8 and ite. Your exception would be ammonium. That's like a common name. I think it's derived from Latin. But you're not going to see ides in polyatomic. You're going to see 8, commonly 8 and ite for your ending. So we're looking at sulfate, sulfite, nitrate, nitrite, right? Now with naming any ionic compounds that have polyatomic ions, you only you name the first element, the metal first, just as you would in the binary ionic world. And then you just name the polyatomic ion second as is. So for instance, and ammonium's your exception. I think most polyatomic ion lists will have ammonium and that's it. Like there are no other common polyatomic ions that we deal with. So for examples, I have sodium sulfate, potassium chlorate, ammonium sulfate there. So you can easily identify there's SO4, there's SO4, that's our sulfate that I talked about up there. We also have a family of, they're made up of chlorine and oxygen, and we actually have 4 of those. I'll list them here. ClO, ClO4. It's the chlorate. It's a chlorate family. So we have chlorate, perchlorate, chlorite, hypo. Okay, so those I would say give it a 99% chance they would be on your polyatomic ion list. And those are examples of polyatomic ions that contain oxygen and then a halogen. So you'll notice that your polyatomic ions typically have oxygen in them. That's a very common theme in your polyatomic ions. So there we have, the CaCO₃, that's your potassium chlorate. That derives from that right there. When it comes to subscripts, that's going to be part of the next section, which is determining your formula, right? So sometimes we need to alter subscripts because we're trying to balance out the overall charge of the molecule. So molecular charge, I'm just going to write this here, molecular charge should be non-existent. It should be 0, okay? We call it neutral, 0, net charge 0, however you want to call it. So if I have, say, a cation that has a +1 charge and maybe an anion that has a -2, we need to balance things out mathematically to make sure our charge is netted out to 0. So sodium chloride, there's an example we already talked about here, Na+1, chlorine -1. Notice it's +1 -1, that nets out to 0. So we don't need to alter any subscripts. We can just put it together like so and move on to the next one. So magnesium bromide, magnesium is group 2. I think let me be more consistent here. +2. And then bromide. So bromine's a halogen, and that'll give us a -1. So notice how +2 and -1, those don't balance, right? We can implement what's called the, crisscrossing the superscripts for your charge, and make it so bromine has 2 and magnesium has 1. And it's a shortcut math method. I mean, you could probably, in just by visualizing it, saying, okay, well, I need 2 bromines to make -2 to balance out my +2 magnesium. Okay, but the crisscross method is something I've seen over the years, and it's sort of fail safe. You can just do it that way, do it written or in your head, and can't go wrong with those subscripts there. So we end up with MgBr2 for the magnesium bromide. Now, aluminum oxide, yeah, I guess I'll stick with blue here. Aluminum, we know, is in group 3, and then oxygen is in group 6 and carries a -2 charge. There's another imbalance, right? We need to crisscross our charges. I forgot to write the numbers down, but yeah. So we have Al2, that's an O, O3. Okay, so for every 2 aluminum atoms, I need 3 oxygen atoms. And you can even double check yourself if you multiply out the charges. This positive charge, right? So 6 minus 6, that nets out to be 0. Okay. Again, it's sort of simple algebra, but if you crisscross the superscripts, for the charges, just move them on down and cross them. You'll get the right information. Now we're just going to reverse. We're going to say KCl. We're going to give it a name now. So we know potassium is K. And then we know chlorine, that's a halogen. And we need to say that we can't see potassium chlorine. We need to drop that ene and add ide. So there you go. There's potassium chloride. We have 2 more left. We have calcium. Ca is calcium. That's a group 2 element. And then we'll just need to flip fluorine over to fluoride. Okay. So notice ene goes to ide. Last one, we have sulfur hooked up to potassium again. Sulfur. Now we're going to change we're going to change that to ide, sulfide. So we have potassium chloride, calcium fluoride, and potassium. Whoa. There you go, sulfide. Now on to the polyatomic ions. We're on the home stretch here. Yeah, tips for success. So ammonium, we know that to be, you would recognize that as a polyatomic ion on your list, and you would say, okay, ammonium is NH4. It carries a +1 charge, and hydroxide, that's OH. So hydroxide is another very, very common polyatomic ion that you'll see in chemistry, and it carries a -1 charge. Okay, so +1, -1, we're good. We don't need to manipulate any subscripts. NH4OH, and we're on. So do you see how important it is? I just want to go back, circle back to the when you take a name into a chemical formula. In the ionic world, you should be putting your charges up there to make sure they match, and then change the subscripts as necessary. So I don't know that we'll even see one here. Let me do the next 2 here. Potassium is K. Chlorite is ClO2. I covered that just a bit ago up here. Yeah, that's chlorite right there. There's chlorite. So yeah, K +1 and then ClO2 -1. We don't need to. That's a 1-to-1 ratio. It balances out, gives you a 0 net charge. So we're good there. Calcium, group 2. Sulfate we know is 2 minus, right? And so that's balanced as well. I should probably do one where we have one that's not balanced, you know, charge wise. So I'm going to write this up here. What if I had, I'm just going to change this over to, if we were to do calcium phosphate. Okay, so, gosh, Angie, learn how to write calcium. Okay, so we would use the same, you know, Ca2 plus. Now phosphate is actually, it's PO4. No, I'm sorry. Yeah, PO4 with a 3 minus charge. Okay, so it's PO4 with a 3 minus charge. Uh-oh, you know, we have a mismatch here, but we can easily cross them over and have, so we'd have 3 here and 2 here. So we'd have 2 calcium for every, sorry, that'd be 3 calcium. 3 calcium for every 2 phosphate. And we have to use parentheses now. So you can't just, you don't want to do this. You don't want to do PO4 2, right? You have to group it, you know, kind of like algebra. You have to group things. So that 2 applies to the entire molecule. I have 2 PO4 molecules in this particular compound. All right. So on the home stretch again, we have, so formula to name, Na₂, that's sodium. And we know SO4, that's our good old friend sulfate. He's pretty popular. Sulfate's popular. You'll see that a lot. Calcium. Calcium paired with CO3. So Ca is calcium, group 2. I'm struggling to write here, guys. Sorry. Calcium. Okay, calcium. And then we have C, carbon, and then 3 oxygens. That's actually our carbonate. Carbonate anion, calcium carbonate. So that is a very common, I think that's present in rocks and sand or something. Yeah, that's a geological compound. So last but not least, we have NH4. We have 2 NH4 molecules combined with a sulfate, or SO4, which is sulfate. There it is again. So ammonium for the first part, sulfate for the second part. So notice that in the polyatomic world, as long as you know, of course, know the name, know the formula, know the charge, you know, as long as you know the name, you just name it, right? You don't need to alter it. The only time you alter an ending is, say, you know, when you're doing binary, you're just doing 2 single elements, a metal, non-metal. You need to throw that "ide" in there, and that's how you differentiate, you know, the 2 types, right? If you see "ide," you never want to put in a polyatomic ion. That's a big no. So here's our final thoughts, and we'll get you done here. Definitely memorize those common polyatomic ions and their charges, and base this off of what is given from your teacher or professor. When you're creating the formulas based on the names, check the charges, make sure they balance out to create the neutral, you know, net zero charge compound. And of course, double check your naming. Make sure you have metals first, and then your non-metals or polyatomic ions second. So this concludes the first video I'm putting out there as far as naming goes. I'll go ahead and put up a place where you can click and go next over to the covalent naming and examples of those compounds. And I hope you enjoy this. If you find value in this particular video and this explanation of ionic compounds and how to name them, please like and subscribe, and I'll see you in the next video. Thank you.